Hello and welcome to the first episode of AstroMagnet. I'm Arush Ramadurai,
And I'm Ishan Chakraborty.
and today we're going to be interviewing Professor Taritree Wongjirad, Assistant Professor of Physics at Tufts University in Medford, Massachusetts.
Welcome, Professor Wongjirad.
So when did you first get interested in physics?
Oh yeah. So well, first, thanks for having me on and and chatting with me. So so my path to physics was kind of indirect. Like I did kind of have an interest in general growing up in science, and I do remember reading sort of popular science physics books like Brian Greene's books and Lee Smollen's book. But I think when I entered college, I primarily wanted to go into biology and was probably thinking that I would go into a career in medicine. And that's because that's what my father did. And I grew up in kind of a smaller town. And so I didn't really know what a career in science could be other than medicine. But then when I got to college, I took freshman organic chemistry. And it's not that it was difficult and it's like, oh, I'm never going to be a biologist or a doctor, but it was. But it's just that the professor there taught it in a very different manner, I think, than what is typically done. He started with the history of chemistry for one, but the second part of the unit was he tried to teach us quantum mechanics, and so that we could understand, the molecular orbitals of the different molecules, and therefore understand sort of the physics behind some of the reactions for behind the organic chemical reactions. And so when he tried to teach us quantum mechanics, that completely confused me. I didn't understand at all what was going on, and that really inspired me then to learn more about it and start to take more physics. And so from there, I started taking more physics classes, and in my sophomore year, I went over to the chair of the department and asked, is there any research I can get involved in, right? And so then I joined a group that was working on dark matter, searching for dark matter using these detectors called noble liquid detectors. And from there, I was basically hooked on doing physics, right? Thinking about, what are the fundamental laws and fundamental particles that exist, and what kind of experiments we can do to try and, fill in the gaps of our knowledge on this subject. We know that our standard model is incomplete, that there are particles out there that we don't understand, and forces such as dark matter and dark energy. And eventually from here, these noble liquid detectors, this technology kind of has a related technology where you can use it to look for neutrinos. And that's the particle I study now. So I kind of drifted over from the dark matter world into doing a neutrino experiment. And there's a lot of open questions there in terms of neutrino physics. And so that's where I ended up. Yeah.
So is your main focus of research right now neutrinos?
That's right. Yeah, so as I said, there's still a lot to find out about neutrinos. So just to, give some background on neutrinos, they're one of the fundamental particles in the standard model. They have no electric charge, and they interact only via the weak force and gravity. So in all intents and purposes, if you want to do experiments, you have to interact with them through this weak force. And as you might guess from that name, that implies that they interact very, very rarely with other matter, right? So the typical statistics is that like a neutrino at energies around those produced by the sun can travel through like a light year of lead without interacting with it, right? Very, very weakly interacting particle. Right. And so, and because of that, we were just kind of having the technology to be able to understand and experiment and do experiments with this particle, with high statistics. But one of the things that folks learned in the last, I guess it's 2 decades now, sort of the beginning of the millennium, is that neutrinos have a very, very small, but non-zero mass. And that was somewhat of a surprise, depends on who you ask. But this discovery has been the focus of lots of particle physicists, including myself, about phenomenon around where does the neutrino get its mass? Because it's possible that the neutrino might get its mass in a different way than the other particles that we know about, and that'd be very exciting. And that's because we're hoping that also that if it's a new mechanism, that will tell us a little bit more about how the laws of physics work, right? In ways beyond ways that we currently understand. We also have a bunch of experiments with neutrinos that show anomalies. So we set up an experiment. We always make a prediction of what we'll see, right? So that we can understand we see something new. And several past experiments see disagreements with the prediction. Some of them see more neutrinos than they expect. Some of them see less neutrinos than they expect. But these are all intriguing, and we see it in several experiments. Now, the answer to all these anomalies is that neutrinos physics is hard, right? You usually can only collect a small amount of events over time, and it could be it's just difficult. But it could also be signs of new physics, right? And so right now, again, we know our standard model is incomplete, and we're hoping that since we don't know everything about the neutrino, maybe it will point us to so some of these new laws that we know have to be out there.
So why should people understand how neutrinos behave?
Why should people understand? So I mean, yeah. Of course, it's just part of the general pursuit of trying to understand, everything that we can about how the universe works, right? It's one of the fundamental particles. It's also one of the most abundantly made particles in the universe, right? So the details of the properties of neutrinos actually have effects that one could, in principle, observe in the sort of structure of the universe, sort of like, what's the distribution of the size of galaxies and how far apart they're spaced. The neutrinos actually, the properties of neutrinos is important in our cosmological model of the universe. In terms of practical applications, right? Neutrinos interact very weakly, and because of that, there might not be applications for neutrinos as of yet, right? I can think of a couple that they're but I should be very clear that they're very speculative, right? So neutrinos, they interact by the weak force, and this is the force that is involved in the decay of radioactive nuclei, right? So whenever you have decaying nuclei, they produce neutrinos, and where you see a lot of radioactive decaying nuclei is in nuclear reactors and things like this. So people have proposed to use neutrinos as reactor monitors. Like you can measure the spectrum of neutrinos and the amount of neutrinos that come. So when I say spectrum, the energies of neutrinos and the number of neutrinos coming out of a reactor, right? And in principle, you can use that to tell what kind of fuel is being burned in the reactor, right? And so we want to make is there a high content of certain isotopes of uranium that produce plutonium, for example, right? You can, in principle, tell if there's a high content of plutonium in a reactor. And so, there may be situations where you want to tell if people are trying to make plutonium in order to make nuclear weapons. One could, in principle, use neutrinos to monitor these things. The even more speculative application is that neutrinos, because they interact so rarely, right? They can be used to point back to objects that are very, very far away from you. So interstellar objects, right? So if for whatever reason, you want to try to communicate between planets. Now remember, right? You have a neutrino which can now travel near the speed of light, but unlike a photon, which of course travels at the speed of light, won't really interact with anything, on its way, to where you pointed at it, unlike a photon, right, which interacts via electromagnetic force, and so it can be absorbed, can be scattered off of dust and things like that. So if you wanted to send a signal, you can try to do it with neutrinos. However, yeah, that is very unlikely from my point of view to ever be useful. But there has been demonstrations of neutrino communications. They have used the neutrino beams at Fermilab to send a little message. It was only several hundred meters, right? And I've heard folks about using neutrinos to communicate between financial centers like New York and London, where I think technically you'd be able to have a slightly faster signal than sending light through fiber underneath the ocean. So if you're trying to do hyper fast really fast high frequency trading, you could use neutrinos to communicate to that. But again, that would be very impractical. Of course, if someone wanted to spend the money to build such a device, that would be a very useful scientific tool, and the community would definitely make use of it to do science. But yeah.
Sounds like
So
some.
you talked about the challenges that go along with detecting neutrinos. Can you talk a little bit about the instruments you use to circumvent those challenges?
Yeah, right.
Detectors?
Yeah, so one neutrino interacts very, very rarely, right? So the way we get around it is we have to make many, many neutrinos. That's one way. And then have all those many neutrinos try to hit a very large target. And in fact, we do both, right? So, we have various sources of neutrinos, but one common source that folks use is to make them via accelerators, where they can make a beam of neutrinos, so a very high, intense source of neutrinos. And then we point them at detectors. So, these detectors are often fairly large. On the small side is the experiment that I work on a lot these days. It's called microboon. It's about the size of a bus, but it contains a very dense liquid, so a cryogenic liquid argon, right? Which is, I think, about 8 times denser than water. But that's kind of on the small side of these detectors. These detectors are getting scaled up to be the sizes of buildings that you put in caverns. In graduate school, I worked on an experiment called Super Kamiokande, which is this 40-meter tall cylinder of water that they hide underneath a mountain, right? So that's so typically when we want to do experiments, we have to make these building size detectors that we fill with some hopefully cheap material, right, in order to be able to get enough events to do the experiments that we want.
So how does the detector help detect the neutrinos or detect the particle interactions?
Right. Yeah. So in general, so the neutrino detectors, like I said, the big thing is like size. So having a lot of nuclei for neutrinos to hit, right, is important. So you have these big detectors. The other thing is that the materials that you fill the detector with have to give you a signal that you can use to see the neutrino. So neutrinos, like I mentioned before, are neutral. They have no electric charge. And because of that, they pass through matter without doing anything, right? If you have like an electron, which has a negative charge, or a proton, which has positive charge, if you shoot that through any kind of matter, like the electromagnetic, that particles interact with the electromagnetic force and leave behind it's going to couple with the matter and leave behind some energy into the material that usually produces some charge and some light, for example. So that's what charged particles do when they move through matter. The neutrinos, as I mentioned, are neutral, and so they travel without a trace through any kind of material. So yeah, so how do you see them? So what we do is we wait for the neutrino to interact typically with the nucleus, and then it will produce a charged particle, right? And then the charged particle then travels to the detector and leaves behind energy in the form of, again, charge and light, which we then can collect and measure, right? And different detectors have different designs to make sure that we can collect that light and charge, either one or both, efficiently, right? And that we can reconstruct the spatial patterns of that energy that's deposited by the particles in order to better infer the properties of the neutrino, right? And so there's, different types of detectors that detect, this information in different ways, right? In order to be able to, find the neutrino events, because, even if you have a big detector, it's going to be the amount of events the neutrinos create are going to be fairly rare, right? Compared to other possible things that can happen. So for example, you have a background where you get, it's a particle called a muon. You can think of it as like a heavier electron, right? But anyway, these muons, they get created in the upper atmosphere and they fall down into the earth. And they can pass through your detector, right? And they'll leave behind charge and light. And so you have to have enough information to be able to say that this is a background event, a muon event, versus, the charge and light pattern that comes out of a neutrino interaction. But another technique for detectors, neutrino detectors, is so they're big, they get the charge and light in a way that they can identify neutrinos, but then you also put them way underground, so you don't have to worry about these kind of backgrounds, and reduce them as much as possible. So yeah, so putting them underground is also a big technique for checking neutrinos.
Experience like a lot of challenges, like detecting neutrinos or like sifting through data.
Yeah, sifting through data can be a challenge because, again, usually the neutrinos are the subdominant component of your data, right? And so to that end, folks are always working on different techniques, right, to do that. So for example, my group, we focus on neutrinos, but a lot of our effort is in trying to analyze the data better, to better find the neutrinos in our data. And the experiment that I said we worked on, microboon, uses a type of detector called the liquid argon time projection chamber, right? That you can think of it as basically a very nice camera that can take pictures of the tracks left behind by charged particles. And so because the data that the detector produces is basically this nice high resolution image, we can use a lot of the machine learning techniques that have been developed in the past 5 to 10 years to analyze the data. These are things like convolutional neural networks, which have been used for natural images to classify them or find particular instances of cats or dogs inside of images. We can use the similar techniques, adapt the similar techniques to find to classify a portion of the image as either being from a certain type of particle or a neutrino interaction, or using these neural networks to identify locations in the image where we think a particle might be or a neutrino might be, for example. So yeah, so that, I think that's one very active area of research across the field, is applying these new machine learning techniques to neutrino physics data. And then at least that's where our group spends a lot of our effort.
What do you feel is the favorite part of your job?
Yeah, I think so yeah, that's many parts that are great. Yeah, I think it's nice to be able to work in a field where you feel like you contribute to some of the fundamental understanding of our universe, right? Of course, that's very slow going, right? It takes several years to be able to, quote unquote, make measurements and say something, new, right? Or just make measurements and see the results of all your work, right? So, results are kind of several years apart. And so in between then, right, it's what are the things that one enjoys about the day-to-day work? And that is, I think it has to be working with, students on different topics, right? Like, like I said, in our group, we work in applying these deep learning techniques to analyzing our data. And so that involves sort of, trying to stay on top of the latest deep learning research, and along with working with students to do that, and trying to sift through all the different techniques and think about, okay, how can we use it, right, to better analyze our data, and then the fact of just trying to implement that, right. So working with a team to sort of stay on cutting edge, trying to keep up with cutting edge research in order to make progress. That's kind of there's no shortage of fun problems to work on, and and they're have luckily a great team of students to work with, so that so yeah, it definitely keeps things very fun on a day to day.
So what advice do you have to students aspiring for a career track in physics or astrophysics or some kind of science, really?
Yeah. Oh man. I don't I would say, I think you should try to get involved with research as early as possible, right? If especially if that's the track that you want to go down, right? Um, you know, don't be afraid, don't feel like you have to wait, to take classes and then sort of be a relative expert before you can contribute to research, right? A lot of the research is not the actual science. Of course, it's important you learn the foundational science, right? And understand like what are the big questions that your group is trying to ask and things like that. It's important to keep track of that. But, solving the problems the day to day, those are, computer science problems. These are all things that you learn on the job. So you should, learning how to apply statistics. Yeah. And yeah, again, these are all things that you learn on the job rather than in class. I mean, you can learn them in class, but I think it helps to just get started right away. And then you also get a sense of like, do you like doing research and stuff like that? So I'd say, yeah, get started as soon as you can on research. And usually groups will, are usually happy to take students on. The other thing I would say is that, to be a good scientist, you got you have to try to generate new ideas, and usually most new ideas are bad, right? And so you got to keep trying to, to do that. And the best way to generate ideas, right, is to read what what people are doing, because it helps inspire. So like, I guess, my advice is to keep track, to try to keep up in reading the literature, right? Like, go and read science papers, and it's tough going. It's not easy. It's not something I need to do more of, right? We all need to do more of, because it can be a tough slog. But after a while, you start to understand a little bit more what the field is trying to say. You understand the jargon and the shorthand and stuff like that. But that's really how you generate new ideas, right? And not just read papers from your field, but also related fields, right? Like, a lot of work that we do now is basically inspired by, papers that come out of computer science. If in order to make progress in physics, experimental particle physics, right, we need better ways to detect particles, right? And so, and new ways of doing that will probably track, in some ways, advances in material science. Maybe there's a new, that it gives you a new way to build a detector, right? That gives you new types of signals, right? So you have to, try to read as much as you can about your field, but then also broadly. That's how you generate new ideas.
Is it okay if interested high school students contacted you for advice and guidance by email?
Yeah, of course. Yeah. Yeah, I'm happy, of course, to try to give advice and things like this. I just want to give a caveat that, professors are very busy, and sometimes it might take a while to get a response, but that doesn't mean, I don't want to respond. I just might take some time to get back. But of course, I'm happy to take questions. And there are examples of high school students working in our lab as well, right? So we're in general, in my lab policy is, if you're willing to put in the time, we're willing to try to find a project for you to work on.
Well, thank you so much for your time. So
thank you.
That was really great. So that was Taritree Wongjirad, and he studies neutrinos at Tufts University. And to learn more about his field, check out his research group website on our website, and we'll be back with another episode.
All right, thanks.